Hello, welcome to Vector's CANape with ADAS option, Reference Camera Calibration Quick Tip. My name is William Merrick, and I will be your host throughout this Quick Tip module. In this Quick Tip, you will learn to execute the Reference Camera Calibration procedure and derive a Reference Camera Calibration file, star.cam, for integration into CANape. As a preface, a few points to consider. The following instructional guide assumes that the user has a basic working knowledge of CANape. For your final reference camera calibration, you should have your reference camera mounted in your target vehicle in its final orientation and position. To perform the reference camera calibration properly, you will need a well-illuminated area for your test vehicle with a large open area that will cover the camera's field of view. Approximately 6 meters by a width of 8 meters in depth is typically adequate, but some cameras have a wider or narrower field of view, so be sure to investigate the visible working region of the camera before performing the calibration. Before we learn how to derive a reference camera calibration, I think it is important to highlight why we may need reference cameras and why they may need calibration. Reference cameras are often used to provide context to vehicle data collected from various ADAS sensors. It is often useful to have one or more reference cameras installed as part of the overall data acquisition instrumentation suite in ADAS applications. The reference camera or cameras are used to understand the environment of the data that is being logged and to provide additional visualization in reviewing and or analyzing the data. To have a spatially accurate reference video, we supply CANape with the technical properties of the reference camera. The purpose of the reference camera calibration in CANape is to properly scale the reference cameras to the mounting environment, set camera resolution, and specify the camera's field of view, and adjust for any lens characteristics such as fisheye. Without a proper reference camera calibration, GFX ADAS objects may not be accurately overlaid in the video window. The CANape reference camera calibration is subdivided into two main and independent components, intrinsic and extrinsic. Intrinsic calibration corrects for characteristics that are internal to the reference camera. The extrinsic calibration adjusts for the mounting orientation and relative position of the reference camera in the vehicle environment. It is important to understand that if the reference camera's mounting position or orientation is changed after the calibration procedure is executed, the calibration procedure may need to be performed again. What do we mean by reference cameras? Well, in the context of this training and the CANape plus ADAS software tool, a reference camera is any video source that implements DirectX interfaces and can be integrated into a Windows operating system. There are some additional common camera options that have been implemented in CANape. For instance, the Vector offers the Axes camera product for direct purchase from Vector, which are compatible with the CANape environment. Once an appropriate reference camera has been properly installed, the CANape reference camera calibration can be performed. Before you begin the dynamic part of the procedure, some preparation is recommended. First, the CCT software is available from within the CANape environment as part of the default installation. Second, you should confirm that your installed reference camera is operational. Next, you will need a chessboard target, which is a black and white checkerboard plane. I will provide the specifics of the checkerboard in the following slides. Third, a generic cuboid test object will be needed. This can be a file cabinet, a cardboard box, or other object that is cubical in nature. The size of the test object should be something larger than a microwave and smaller than a refrigerator. Lastly, you will need a digital or analog tape measure to measure the distance from the test object to the reference camera, as well as the position of the reference camera to the test vehicle. The checkerboard or chessboard target object is necessary for the reference camera calibration routine. Here are the requirements and description of an appropriate chessboard target object. A black and white low glare target is needed to obtain a clean calibration image. The larger the checkerboard, the better the final calibration quality will be, but will also require a more carefully executed calibration. We recommend an approximate chessboard dimension of 1 meter by 1 meter. A rigid chessboard is needed to ensure planarity of the target object. Target objects that bend while the calibration images are being taken will have a negative influence on the quality of the calibration and may even prohibit the completion of the calibration routine. The subsquare or tile minimum edge dimension is 5 centimeters. The black subsquare edges should be crisp and not blurry. Here are some additional details and terminology regarding the chessboard target. Rows are defined as horizontal tiles. Columns are defined as vertical tiles. The overall chessboard width and height are from the outer edge of the first tile to the outer edge of the last tile, including the white tiles. The tile edge length is a subsquare dimension. In this example, the tile edge length is 5 centimeters. As you begin to step through the camera calibration procedure within CANape, you will notice that there is text written in blue, and pressing these will pop up additional details or definitions that may be helpful. Before we begin the camera calibration routine, we must first prepare the CANape environment for the camera calibration tool. Assuming the reference camera has been properly installed and is operational on your host PC, we can set up CANape, start CANape, choose a new project or an existing project that you may be configuring for your work. Next, configure the reference camera or cameras as a recognized device in CANape. To do this, go to the Device menu at the top and choose New Device from the ribbon. This will open a new window called New Device and prompt you to select the device type. Choose Video, Camera AVB, and then choose Context Reference Cameras. Move to the next step by pressing Next. Before CANape can use the CCT to perform the reference camera calibration, we must prepare the CANape project for access to the chosen reference camera or cameras. After pressing Next, you will be prompted with a new window with some settings for the reference camera, and in this example I have chosen the Logitech webcam already installed on the host PC, where there are some camera-specific settings that I can modify, such as resolution. After reviewing and modifying, if necessary, the camera-specific settings, press OK, and CANape will attempt to connect to the device at this time. If there is an issue communicating or establishing connection with the device, CANape will prompt you with an option to continue offline. The reference camera device is now added to the CANape project and should be visible in the Symbol Explorer under Devices. Right mouse click in the CANape Graphical Interface tab and choose ADAS window, Video window from the drop-down menus. Finally, left mouse click and hold the new reference camera device and drag it to the video window and drop. Now, we are ready to open the CCT within CANape and begin the calibration procedure. To do this, right mouse click on the video window and select ADAS System Configuration. The ADAS System Configuration window will give you access to the CCT via the Camera Calibration Files section. Next, click on the chessboard symbol to open the CCT. This will open the CCT home screen and you are ready to start the calibration procedure. It should be noted that if you have already performed a camera calibration and the resulting star.cam file is stored with the project, you will not be able to start the intrinsic camera calibration from the beginning. Simply remove the existing file shown in the field by pressing the X to the right of the star.cam file name. Depending on the existence of a pre-existing cam file calibration, you will be presented with this window. Press the Start Camera Calibration. Step 1 of the intrinsic camera calibration, the user to select the reference camera to be calibrated from the drop-down menu. If you cannot find your target camera from the drop-down list, then abort the camera calibration and correct the installation of your reference camera. Step 2 of the intrinsic calibration configures some camera-specific settings such as resolution, autofocus, and fisheye. Depending on the camera, some or all of these settings may have been previously configured and the chosen settings should be visible in the fields. Otherwise, select them at this time. Once selected and confirmed in the step, you should not change these settings because it may result in an invalid camera calibration. In step 3, you will indicate to CANape the properties of your chessboard. You will need to enter the number of rows, the number of columns, and the tile edge width. The overall dimensions of the chessboard target will be calculated from those entries. When finished, click Next to proceed. In step 4, you will collect the images for the camera calibration. You will need your chessboard target and the vehicle position such that there is a free space in the field of view of the camera under calibration. As described previously, the data for the calibration calculation consists of a collection of images where the quantity is entered in step 4. We recommend 15 to 25 images be used in the calculation. The images can be collected individually using the One Snapshot option or through a pseudo-automated sequence by selecting Start Series button. If you select the series method, you will be prompted to enter two parameters of the series, snapshot count and time in seconds. The snapshot count is the number of images to be used in the calibration, and as mentioned earlier, we recommend 15 to 25. The time in seconds is the number of seconds between snapshots. Depending on your ability to reposition the chessboard between snapshots, you should enter an appropriate duration. We recommend 3 to 5 seconds. When you are ready, click OK and the image collection sequence will begin. The CCT tool will show you the snapshot timer in the case of series method and the number of acceptable images recorded so far. We recommend that you position the display of your PC with the CCT GUI visible such that you can monitor the status of the image collections as you execute. Here are some tips for a successful camera calibration. Position the chessboard at various positions and orientations across the entire field of view of the camera, both vertically and horizontally. Vary the distance from the camera to the chessboard target object as well. Include orientations that cover the full field of view of the reference camera. Use ample lighting. Avoid glare on the surface of the chessboard target object. Try to keep the chessboard target as still as possible when the image is being taken. Images that are determined to be viable in the calibration calculation will increment the sequence counter. It is typical for some images to be rejected for various reasons. As long as you eventually acquire the preset number of images, there is no reason to worry about some rejected images. Here's an animation of someone positioning the chessboard target at various positions in the camera's field of view. The animation doesn't show this, but be sure to also change the angle of the chessboard target relative to the camera in all three axes, pitch, roll, and yaw, but not so much that the chessboard is not fully visible to the camera. Once you have reached the prescribed number of calibration images and the acquisition is complete, and now you have an opportunity to review the collection of images and view some preliminary feedback regarding the viability of each image. We recommend that you review the images such that you may understand why a low quality or unacceptable calibration was calculated, and then change the positioning of the chessboard target in a repeated step 4 if a higher quality result is needed. Before clicking next in step 4, review the images. Good images will contain green dots over most of the vertical and horizontal fields of view. You can review the images individually by selecting the image from the right side of step 4 window. The lines drawn on the images should connect subsequent rows and is an indication that the CCT can resolve the checkerboard pattern fully. With the images reviewed, you can now click on the Next button, which will proceed to step 5 and trigger the calibration calculation. This may take a few seconds to complete, but once Next is clicked. When the calibration calculation is complete, the top box will indicate the calculated quality number in percentages. We have found that 40% or higher is an acceptable quality result for most applications. From this page of step 5, you have the option to recalculate the calibration with the alternative fisheye lens selection, meaning perhaps your camera does or does not have fisheye but was selected wrong in the first place. If you still cannot achieve 40% or better quality, repeat step 4 and change the manner used to position the chessboard target or increase the resolution of your reference camera. Here's an example of a poor image and a good image. With the completion of step 5, the intrinsic camera calibration is complete. You should be able to locate the star.cam file in the project folder. The default star.cam file name will include the chosen camera resolution. This file should be stored in a location that is available to the CANape project and should be visible in the ADAS system configuration window within the camera calibration file selection. You can now proceed to the extrinsic portion, which contains 2 primary steps, 6 and 7 overall. You will need to have your test object available to start the extrinsic calibration. The test object needs to be cubical and square in nature. We recommend an approximate dimensions of 1 meter by 1 meter by 1 meter. Items like a cardboard box or a file cabinet or tool chest are acceptable objects. Choose your test object and then measure the height, width, and depth. Place the test object approximately in the center of the field of view of the camera such that either the left or right vertical edge is aligned with the vertical crosshairs displayed in the live camera image in the Step 6 CCT window. Next, measure the distance from the reference camera to the nearest front side surface of the test object. This will be the Y value. Measure the distance from the reference camera to the leftmost vertical edge in the x-axis, horizontal or lateral, of the system diagram. Finally, measure the distance from the ground where the test object is resting to the reference camera vertically. This is the Z measurement. Enter the measured X, Y, and Z values into the 3 topmost fields of the test object entry table. Then enter the measured dimensions, width, depth, and height of the test object into the test object fields labeled width, depth, and height in meters. If you are unable to accurately measure the reference camera directly but have pre-existing measurements between the reference camera and another global reference point of the test vehicle, you can enter those alternative X, Y, and Z values in the X, Y, and Z offset fields of the coordinate system box. If this data is not available, estimates can be entered into the field for linear offsets and rotational offsets. Later, when you are setting up CANape GFX graphic overlays, you can apply further adjustments real-time or to previously recorded data to better compensate for any final adjustments needed. To properly understand the orientation of the CCT coordinate system, here is a description of the linear offsets on their coordinate system. Z is vertical, Y is forward in the vehicle, and X is lateral. Here's a description of the rotational offsets on their coordinate system. Z is a clockwise rotation about the vertical axis. Y is a clockwise rotation about the front of the vehicle. and X is a clockwise rotation about the right side of the vehicle. Rotational offsets can have a large effect on the final placement of graphical overlays. Here's some final notes regarding the extrinsic calibration. A correction with offsets and angular rotations will not replace or compensate for a low-quality intrinsic reference camera calibration. Once the extrinsic reference camera calibration is completed, do not move the camera or you will have to redo the extrinsic. The derived extrinsic offsets and rotations can also be specified directly in the ADAS system configuration of CANape. If you have a measurement project for multiple vehicles where the camera position is not identical, we recommend specifying the extrinsic values in the CAM file. This can be stored per vehicle. Both the star.cam file and the values entered into the ADAS system configuration are stored in the measurement file when the measurement is saved. This concludes the quick tip. I hope you found it useful. Thank you.